right? So you have x transpose, it's like x times p times x. What will be the second derivative? It's 2 times p, right? So this derivative, the Hessian of this will be 2 times p. Of course, we have a half there, so 2 cancels, we have p. And then b transpose x, it's linear in x. So if I take the second derivative, what do I get? 0. Constant anyway, 0. So I get p. So now, if it has to be convex, then this is what you need to have, right? It should be positive semi-definite. So if the matrix P is positive semi-definite, the quadratic function will be convex. On the other hand, if it is implies F convex. On the other hand, if it is negative semi-definite, it's concave. That's all. What happens if it is equal to 0? I mean, meaning it's equal to 0, meaning it's a line, right? You will only have b transpose x. What kind of a function is b transpose x? It's a straight line, right? Hyperplane. Hyperplane is what? Convex, concave? It's both, right? Both concave and convex, right? Okay, is this clear, everyone? Got it? So you have the convex function now, right? So now let's I think we should soon get into the algorithms, right? That's what you will actually write in your let's say if you look at your how many of you have used TensorFlow or something like that? It's okay, I won't ask any tough questions or anything, don't worry. Have you used TensorFlow for neural networks? Right? No? Okay. Of course, the way you fit a model is there is something called model.fit, right? So it will do everything for you, right? A high school student can do it, right? But what goes behind that is what we should understand, right? As engineers. So there is something. So when you do model.fit, you should also tell how you are going to optimize your neural network. What do you mean by that? What kind of an algorithm I'm going to use? So you pass what is known as SGD, right? Stochastic gradient descent, right? Well, let's for a moment, don't worry about stochastic. Let's only look at gradient descent, right? Let's understand gradient descent. That is good enough to understand stochastic gradient descent. All that you have to do is, you take a course in probability theory and to figure out how to handle that small random fluctuations. But otherwise, it's gradient descent only. Okay, let's see. In order to understand that, first of all, we will look at a few things, right? So in the last class, we looked at what do you mean by strictly convex and convex, right? Instead of greater than or equal to, you have greater, it will be strictly convex. Okay. So now let's see if it is strictly convex, whether you will have a single minima or global minima or multiple global minimas, right? Let's look at that. Okay, fine. So let me write it as a theorem. Let's try and see if we can prove it. I'll do it for maybe I'll do it for a general case. Rn to R be a strictly convex function. Strictly convex function. Then there exists a unique global minima. Okay, there exists a unique global minima. How do you prove this? So essentially, I'm saying the function looks like this. This is how it looks like, but not like this, right? This can never happen, right? Well, nor this can never happen. Both are at the same level, right? So how do you prove that this is true? What is your? I think I. So next class is philosophy or previous what? You have philosophy class today. So how do you argue out, right? This is true. That's where logic originated, right? Ancient times. So, right. So how do you argue out that you cannot have two global minimas when it's strictly convex? Any thoughts? How do you argue out? First of all, It's very intuitive, right? If you have strictly convex, you should have only one global minima.